Hello everyone, myself Dr. Santimay Kundu. I welcome you. Lecture 3 of soft computing techniques. Till now, we covered fuzzy sets and membership functions, alpha cut of a fuzzy set, convex fuzzy set, fuzzy subset and scalar cardinality. So last class we discussed about the scalar cardinality. So let's start with some properties of scalar cardinality. So scalar cardinality is that we define scalar cardinality of a finite set. Scalar cardinality of a finite set of a finite fuzzy set A is defined as that mod of A equal to summation x belongs to the universe set x mu A x, that is sum of all membership functions. So number one property is that if for all k then cardinality of V should less than equal to cardinality of A. I mean for each element the membership functions of B is less than equal to the membership function of A. So cardinality of B should less than equal to the cardinality of A. So let's the proof of this. So as you know, the cardinality of B is, so the proof of this. As you know, the cardinality of B can be defined as summation x mu A mu B xk. So each mu B xk should be less than equal to given that. So the summation also less than equal to mu A xk. So that is equal to A. So this is the proof that if each membership value of the fuzzy set B is less than the membership value of fuzzy set A, then the cardinality of B should be less than equal to the cardinality of A. So that is the property 1. Now property 2 is that complement of cardinality of complement set A should equal to the number of element in the universe set minus A. Okay, so you know the mode of cardinality of this is summation k equal to 1 to n mu A bar xk. The same thing can be written as summation k equal to 1 to n 1 minus mu A xk. So this is the number of element, that is n minus summation k equal to 1 to n mu A xk. So that is the number of element of the universe set X minus cardinality of A. So we have proved that cardinality of A complement is the cardinal set, total cardinal set, universe cardinality of universe set minus A. So now try to understand the relative cardinality. So relative cardinality is that the term relative cardinality is defined as the term relative cardinality is defined as that A, then again another so that is written as number of A by number of X. X is the universe set. Okay, so now for any fuzzy set A, for any fuzzy set A, this number relative cardinality is lies belongs to 0 to 1. So if it is 0, if relative cardinality is 0, Then if it is 1, then you can say that mu a xk equal to 1 for all k. So you can say that if mu a xk equal to 0 for all k, then cardinality is 0. If this is 1 for all k, then it will be the 1. So that is known as the relative cardinality and its some property. Now we know that we have studied that each member in a fuzzy set is associated with membership functions. So we have studied some membership functions. Now we are again try to introduce some more membership functions as per the given below. So here variable is x, ABC is known as parameter. Here ABC are parameters. So with property that we are saying that A is less than B less than C. Now the triangle. So let this is the x, this is the mu x. So let 3 point A, this point is B, this point is C. So this is some value belongs to 0 to 1. So this is the triangle. So here we can write this triangular membership as, we can write the triangular membership as this is triangle x ABC. This is equal to 0 if x is less than equal to a. This is equal to x minus a. If you find the equation, you will get it, x minus a, b minus a. If it is lies belongs to a to b. If x lies belongs to a to b, this is equal to b minus d minus x by c minus b if it is lies belongs to b to c, and this is equal to 0 if x greater than c or x less than x. So that is known as the triangular or triangle parametrize of the fuzzy set. So here you can set the example some let x denote the number of bedroom, x denote the number of bedrooms for 4 persons, and mu x denote the happiness. Mu x denote the happiness. So if the number is if b equal to 4, then will the maximum happiness, it depends. So let assume that less than less happiness, like that. If number of room is more, then also they will not be happy. So this type of example you can set. So that is the triangle membership function. Now trapezoid. So here the same thing, a b c d are known as parameter with the condition that a b is less than d. So that is trapezoid. So you can draw the diagram like x, and this is mu x. So 4 points are there, a b c d. So let at b it is 1. So let this is the diagram. This is the diagram a b c d. So here mu x can be written as, this is equal to 0 if x is less than equal to a. This is equal to the straight line, the same as it is. So it is x minus a by b minus a. So if x lies belongs to a to b, this equal to the 1. Suppose this value is 1. This value is 1, suppose. So that will get it if b less than equal to c less than b less than equal to x less than equal to c. This is equal to d minus x by d minus c. So that is x belongs to c and d, and this is equal to again 0 if x is greater than d. So this is the trapezoid. So you can take one example. Suppose we consider that x variable is the age, x is age, and mu x, the fuzzy set is denote the x denote the set of young age. So here you can say that if something like 15, a equal to 15, so that will be, or a equal to 5, that will be the child. Now from 5 b equal to b to c, suppose it is 25 to 35, then it will be surely young age. After that they are going to old. So that is the x, you can say the set of young age can be represents the in terms of Taffy chart. Now next is the Bell function. So Bell function is just like the here you can see the Bell x equal to Bell x abc. This can be written as 1 by 1 plus x minus c by a whole to the power 2b. So it's graph like these things. The shape is Bell. Okay, shape is Bell. So here you can say C is the center, A is adjusted to vary the width, and B control the crossover point, mu x like that. So this is the suppose 0.5, so this B control that slope of that crossover points. So here example you can say the x is the number of pupil and mu phi x is denote the income of persons. So there will be very less people income, the less income. There also income is more, that will be the also very less person is there. Medium incoming mid something more people are there. So that is the some example of the fuzzy sets. Now symmetric fuzzy sets. So symmetric fuzzy sets is that a fuzzy set A fuzzy set A is symmetric if its membership function, so I am writing it if membership function is symmetric about a certain point x equal to c, such that mu a c plus x equal to mu a c minus x for all x belongs to the universe set X. I mean, this diagram you will get like symmetry. So that is X, this is mu X. So that suppose this is triangle X equal to C here. So suppose this point is something, this point. So it is, suppose these two are equal distance. So that you can say that this value is 1. So you can check this is the symmetric fuzzy sets. Now we are going to teach some basic operations on fuzzy sets. So first is union of two fuzzy sets A and B. So that is very simple thing. So let A is a fuzzy set. So that is, you can write it X mu A X, and B is a fuzzy set. That is, you can write X mu B X. So now union of two fuzzy sets A union B. So let's C equal to A union B. So this can be written as C, this fuzzy set C can be represented as X maximum of mu A X mu B X. So membership function of C, you can write that membership function of A mu, that is C, X is equal to the maximum of mu A X mu B X. So let's try to write one example. Suppose A equal to, we are writing very simple, is 1 0.5 2 0.7 3 0.9 4 1. B equal to, some element may be common, may not be common. So suppose 1 0.8 2 0.6 3 0.5 4 0.2. So A union B, so one maximum of these two, 0.5 and 0.2, compare it, you will get 0.8, 2 0.6 0.7, so that is 0.7 maximum, 3 is 0.9, and 4 1 and 0.2 1. So that is the union of two fuzzy sets. Okay. Now there is one theorem: if D is any fuzzy set contain both A and B, then it also contains the union of A and B. So what is that? D contains. So A is a subset of D, B is a subset of D. We need to prove that A union B is also a subset of D. So need to prove it. So check the proof. So it's proof. So it is given that A is a subset of D. So you can write that A is a subset of D. So as A is a subset of D, you can write mu AX is less than equal to mu DX, and mu BX is also less than equal to mu DX. Now the mu of A union BX, that is equal to the maximum of mu AX mu BX. So this should also the less than equal to mu DX. So we can say that A union B is also the subset of D, or D contains both union of A and B. Okay. Now try to understand the intersection of two fuzzy sets. So one fuzzy set A, another fuzzy set is B. So the intersection of two fuzzy set is A union B. So that is suppose A is a fuzzy, same way A is a fuzzy set, that is X mu AX. B is a fuzzy set, that is X mu BX. So A intersection B, that is also the fuzzy set X, and it is the membership come from minimum of mu AX mu BX. So you can write that membership functions of A intersection BX is the minimum of mu AX mu BX. So if you try one example, then you can write that, let I took any example, A equal to, take two value, that 1 0.1, 2 0.5, 3 0.7, 4 0.9. B you can take 1 0.9, 2 0.7, 3 0.5, 4 0.1. So the A intersection B will be 1 minimum 0.1, 2 0.5, 3 0.5, minimum of 0.9 and 0.1, so that is also 0.1. So this is the intersection of two fuzzy sets A and B. Now there are some properties of fuzzy sets. So first time write the commutative. Commutative is simple, that A union B equal to B union A. A intersection B is equal to B intersection A. Okay, so you can write it 1, you can write it 2. Now associative, so you know that is A union B union C is equal to A union B union C. Similarly, A intersection B intersection C equal to A intersection B intersection C. So you can write it 1, you can write it 2. So that is commutative, and this is associative property. Now distributive property. So distributive property takes that A union B intersection C is equal to A union B, then intersection of A union C. Similarly, you can write A intersection B union, so B union C whole intersection with A, that you get A intersection B union A intersection C. So this is known as the distributive properties. So now idempotent. So A intersection with A, so that you will get A union A, you will get A. Similarly, A intersection A, you will also get A. Suppose that phi is empty fuzzy, phi will get A. A intersected empty fuzzy set phi, you will get this is as phi. So this property is also known as the idempotence property. Now transitivity. Transitivity is that if A is subset of B and B is subset of C, then A is also a subset of C. Then the next part is involution. So complement of A, the whole complement, we again will get the A complement. Okay. Now De Morgan's laws. So first is that A union B complement is equal to A complement. Now sign change, intersection B complement. And second is that A intersection B complement is A complement union B complement. So that is the De Morgan's law. So these are the some laws or some properties of the fuzzy set. Now we can prove all the properties. So we are going to prove the sum properties. So suppose we are proving that commutative or distributive or associative. So let us first to prove the associative property, which is that this is equal to A union B union C. So we are going to prove these things. Okay. So all are fuzzy sets. So without without loss of any generality, we are assuming that mu x is less than equal to mu bx is less than equal to mu cx. Okay, so there are three fuzzy sets A, B, C. We are assuming this A mu A less than x, mu B less than x, mu C is less than x. So without loss of any generality. So we are assuming without loss of any generality. Okay. So now that A, so consider these things. Consider A union B union C. So that can be written as that maximum of mu Ax, then again maximum of mu Bx mu Cx. Now the maximum mu B and mu C, definitely the mu Cx, we assume that. So mu x and mu Cx. Maximum of these two is mu Cx. So write this is equal to 1. Now consider the other side. So consider the other side, which is A union B union C. So that is again the maximum of mu Ax mu Bx and mu Cx. So the maximum of mu A and mu Bx is mu Bx and mu Cx. So maximum of mu B and mu C is mu Cx. So that is equal to 2. Now from 1 and 2 we can consider that A union B, B union C with union A is equal to A union B with union C. So that is the one property. You can check the other property like commutative and that. So we are again going to prove the associative property. Okay, so associative property is that A intersection B union C is equal to A intersection B union A intersection C. So we are proving that. You can check the other one also. So consider this side. So without loss of any generality, we are assuming the same thing. Mu x is less than equal to mu bx is less than equal to mu cx without loss of any generality. So that this is equal to minimum of mu ax, then maximum of mu bx mu cx, because this is union, so that is minimum. So now you can write minimum of mu ax, maximum of mu b, say mu cx. Now you will get mu ax. So write this is equal to 1. Okay. Now try to understand the other side, that is A union A intersection C. So this is equal to, you will get it, that maximum of minimum of mu ax mu bx and minimum of mu ax mu cx. Now you will get minimum of mu A and mu b is mu ax, minimum of mu x and mu c again mu ax. So we will get it mu ax. So it is 2. So from 1 and 2 you can check, from 1 and 2 you can check A union B, A intersection B union C is equal to A intersection B union A intersection C. So by the other thing you can also prove. Now try to understand the proof of De Morgan's laws. So we are proving one thing. We are proving this property, A intersection A union B complement equal to A complement and B complement, A intersection B complement. Okay. So without loss of any generality, we are assuming that mu ax is less than equal to mu bx, right? Okay, so 1 minus mu ax is greater than equal to 1 minus mu bx. Okay, so we have these things. Now mu of A union bx, so it should be equal to 1 minus mu of A union bx. So this should be equal to 1 minus maximum of mu ax mu bx. So now as mu ax is less than mu bx, so maximum is mu bx, so you will get 1 minus mu bx. Okay, now consider the other side. So now consider other side, which is A B. So it is basically so mu of A bx, this should be the equal to the minimum of mu A bar x and mu b bar x. So that is minimum of 1 minus mu ax, 1 minus mu bx. Now 1 bx is less than minimum, so it is 1 minus mu bx. So you can assume this is 1, this is 2. So from 1 and 2, we prove that from 1 and 2, we prove that these things. Okay. So similarly, you can prove the other De Morgan's law. Okay. So now the conclusion we have today, what we have learned. Today we have learned, first we solved some question based on cardinality. So we have understood some property of scalar cardinality. We have understood some membership function like triangle, trapezoid and bell with example. Second, some two basic operations, union, intersections, some properties and with proof. Some properties of the basic operations, some properties with their proof, with proof. So now I am giving one question. So try to solve this question, which is that let X is the universe set which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and A equal to Fuzzy set A equal to 1, 0.2, 2, 0.5, 3, 0.8, 4, 1, 5, 0.7, 6, 0.3, and B is 1, 0.3, 3, 0.9, so here 2 is 0, 3, 0.9, 6, 0.8, 7, 0.1, 8, 0.4, 9, 0.6, 9, 0.6, 10, 1, 10, 1. So question is that first to prove A union B, find A union B, find A intersection B, and lastly prove that cardinality of A union B plus cardinality of B intersection A or A intersection B equal to the cardinality of A plus cardinality of B. So prove these questions. So these are the references for today's class. Thank you.